Hi, this is Ricardo Jimenez, and I'll be showing today our lesson on lab practice number 2, designing a programmable relay timer. In this practice, you will build a timer that is triggered with a push button, and it will generate an n seconds pulse to control a relay, where n is a byte defined by the 8 position dip switch connected to port C. So, and we will have a resolution of 1 second. Okay, and this is a timer. Right here you can see in this PIC micro, the 1619. And we have port C as the port that programs the amount of time that we want to control this relay module. The RC0 is the least significant bit, and it has a binary weight equal to 1. So the binary weights are increasing by 2 to the n. So we have 1, 2, 4, 8, 16, 32, 64, and 128. So you close them all of them at the same time, all of them, that will be 0. So when a closed switch will be a 0 logic and an open switch will be a high logic, because there are the internal resistors, RPUs on port C, and they are enabled and they are integrated, embedded in the micro. That's why when you open the switch, the pull-up resistor makes this floating pin, it makes it a 1. So, and the timer will be triggered by this push button, an normally open push button, connected to RA2. Notice that this push button doesn't have external RC network for debouncing, but the debouncing will be a delay, 20 or 30 milliseconds delay that we will add once it is triggered. We will not use the practice selector in this case. So we have the relay module and a piezo buzzer, a beeper. This beeper will be beeping every second to indicate that the time is transcurring and the time is increasing, and that way we know that the micro is alive and kicking. But every pulse will be a 5 milliseconds pulse, because we don't want this beeper to be annoying when the timer is working. So to create the pulses in the timer, in the beeper, instead of making pauses of 1000 seconds where n, so right here you can see a 4 next loop. This is a 4, this is a next loop. So for every 4 there must be a next. So we increase 1 to variable I from 1 to n, where n is a maximum number of times, is a maximum time that is programmed. So we could create here a 1000 pulse, 1000, which is equal to 1 second. Instead of doing that, we reduce 5 milliseconds from this pulse and we add another 5 milliseconds right there. First we turn the beeper, and then we add 5 milliseconds, and when we turn off the beeper. So that's how we create that 1 second. 995 plus 5 is 1000 milliseconds. And also right here, if we want to stop the process at any time, we can add this instruction, because sometimes you need to stop the timing period at any time. And so if the user presses the push button in the middle of any period of time, this one will go to finish. It'll clear, or it'll stop the process. Okay, so the code starts here, and I'm coloring this in different ways so that this is just the introduction. Well, today's date is different, and master clear goes to 5 volts. This is a programmable timer using this PIC, and tries in this yellow, highlighted in yellow instructions, I'm making port C as an input and ansel C equal to 0, so it'll be a digital input. And for port B, I'm making here the tries B equal to zeros and ansel B equal to 0, so port B will be a digital output because we are using RA0 and RA1 as outputs for relay and the beeper. In this color here, tries A and ansel A, I'll notice that I'm making RA0 and RA1 outputs, and the rest, RA2 through RA7 or through RA5, because we know RA6 and RA7, they don't exist, they are made inputs. And right here on cell A, we want to have all port A digital because we're not reading voltages, right, from any sensor or any trim pod. Now we enable all pull-up resistors with this instruction, option underscore reg.7 equal to 0. And then we clear all latches on the ports. We're not reading those latches, no, we're not using them. And then we enable the RPU on the pull-up resistors on RA2 only, because this is RA0, RA1, RA2, because right here is a push button, okay, and it requires just one resistor. Only that pin requires the pull-up resistor, not the rest. On WPUB, I'm selecting the 4 resistors, the pull-up resistors, even when we're not using them. And port C, I'm using all the resistors. I'm enabling all the resistors because right here are the micro switches, as I explained in the beginning. And the switches are here. Right here, all the switches are here, and all the resistors are right here internally to voltage, the pull-up resistors on port C. So, and finally here we select OSCON equal to 6A hexadecimal to work at 4 megahertz clock. OSTUN equal to 0. We declare two variables, two variable byte variables, which are named I and N. So RPT is our starting label, and right here in RPT, let me move here the illumination. Okay, so we have here RPT is our first label. We clear 3 ports with this instruction. Okay, so we make sure all ports are equal to 0. Then we have the stay label, and we ask for the push button. If port C.2 is equal to 1, then go to state. So if the push button is open, the micro is waiting for the user to press the push button. When that happens, when the user is not pressing the button, the micro will go to stay label. So will be looping here forever, waiting for RC2 to go low. So when the user presses the push button, RC2 goes low, and so the micro gets out of this loop, of this condition, and then it goes right here. So, and right here, the port C, the reading on port C is transferred. The contents of port C are transferred to N. We wait 30 milliseconds. That's optional. And then we have to ask if the user didn't select any time. So if N is equal to 0, we have to go back to state. We have to start again because we can't have an output period equal to 0. So that's invalid. So it has to go back to state to wait for a new reading, waiting for N to be different from 0. If it is different from 0, then we turn on the relay right here, and on port A.0, let's see what is on port A.0. Yeah, we turn on the relay on RA1 is a beeper. Okay, so right here on port A.1, where were we? Okay, we were here. We turn on the relay right here, and then we have to select the time. We have to make loops for the time. So how long is this relay going to be activated? So depends on the number n. So we turn on the beeper, the relay and the beeper. So we wait 995 milliseconds, and then we turn on here the beeper, and we wait 5 milliseconds, and we turn off the beeper, so the sound will be only for 5 milliseconds. And if port A.2 is equal to 0, then finish. So if the user wants to stop this process, he will press the push button again in the middle of the period, and it'll go to this label, and it'll finish the process, clearing port B, and a pause for 1 second. Okay, and that way we don't have any output. So, but if the user doesn't stop the process, so the micro will be looping right here, because it'll perform this 1 second. So 995 plus 5 milliseconds is 1 second, and then it'll have the next I. For every 4 there is a next, 4 next loop. So I is incremented again and goes back to here, looping n times. So we have here n equal to 5, so we will do this 5 times. When it is equal to 5, it'll get out of this loop and it'll finish the process. Okay, notice that we are clearing here port A. Well, I place here port B, but it is port A. We are clearing port A, then we wait 1 second, so we pause 1 second, and we start a new timing cycle by making an unconditional jump, which is to go to this label, go to RPT. So we clear all ports and we start the process again. So notice that this is the time, the period of time, and this time was read. The variable n got its value from port C. Okay, so it is a simple program, and you can make, of course, many changes to this code. So the assignments that I'm giving today are this. So modify the code to increase the range to up to 1023 seconds. So what I'm asking here is increase the number of bits on the switches on the input right here. So you have RC0 through RC7. Now you need RC8, RC9. So we don't have it, but you can get them from here. You can get it from RB6, RB7, and you can use these 2 switches, or even these 4 switches, to increase the time from 8 bits to 12 bits, or from 8 bits to 10 bits if you only take 2 of these or these 2. Okay, that way you can increase the range. With 10 bits, you will increase it to 1023 seconds. Okay, with 11 bits, 2048. With and then the next one will be 4096. So student assignment 2, design a timer within the range of 1 to 255 milliseconds. So the binary weight in this assignment will be 1 millisecond up to 122 milliseconds. So the least significant bit will be in milliseconds. Okay, if you do that, you have to write the code, compile it, and of course you have to change the number of pauses, and this pause you have to change it, and of course you also need to change this one. So you might want to decrease them to 1 millisecond for the beeper. It's up to you, okay, to find that solution. And there is another student assignment 3, which you can read it But at this time, I'm leaving this homework to all of you. Student assignment 1 and student assignment 2. Okay, that's all for today. Thank you.